Okay, let's get started. So should have two handouts. Today I want to talk about hydraulic conductivity. What I want to point out though is the last class when we were talking about porosity, we went up through secondary porosity and we talked about typical values of porosity. There are two other terms that are related to porosity. One is specific yield and the other is effective porosity. Those are going to be important parameters and they're really part of the last lecture. So what I'm going to do is make a supplementary recording that describes those two things, and you can watch that on your own. That'll allow us to start with hydraulic conductivity and get through that topic today. Okay, so I'll let you know when that supplementary video probably be about 10 minutes long.
Dr. Murdoch.
So here's what I want to talk about today: hydraulic conductivity. What it means. We'll look at an analog for hydraulic conductivity that'll be flowed through a capillary tube, some typical values, and then differences between hydraulic conductivity and permeability, and some also introduce the topic of anisotropy and how you can work with that. So hydraulic conductivity, recall we saw that in Darcy's law, right? So Darcy's law is, so flow in X direction would be that the head gradient in the X direction, it's going in the opposite direction, so it's going down the hydraulic head gradient, and this is the hydraulic conductivity here. I'll use capital K to mean hydraulic conductivity, and we can see from this that it's the first time we saw it was in Darcy's law, and really this is where it's defined in Darcy's law. Okay, so if we were to use the definition from Darcy's law, we would say that it's the ratio of the flux to the head gradient. Okay, and that's really what I think of as the definition of hydraulic conductivity. If you, I don't know, if you ask ChatGPT, it'll give you some kind of a different explanation, or different definition, something like the resistance to flow or something like that. But this is where hydraulic conductivity is defined in Darcy's law, or this is where it exists. This is the reason it exists. So we'll think of it in this format. All right. So ultimately, it's going to be, well, then what we saw from the definition is that it's going to describe the ratio of the flux to the hydraulic head gradient. And that is going to be, that'll be a measure of the resistance to the flow through porous media. So let's take a look at how this works. And I want to start off with a simulation of flow through porous media. So there's the scale. And this is a photomicrograph of some porous media. And that's the grain right there. The white stuff is the grains, and the pink is the pore space. And so this is a slice through the porous media and a photograph of that slice. And this has been put into a model where we can go and do a simulation of flow through the pink space at this small scale. So the total size of this is probably less than a millimeter. So the way you do that kind of thing is you take the entire space where the flow is going to occur, and you put in a a finite element mesh, these triangles, and that allow you to do the calculations that you need to simulate the flow. We'll do that stuff later, but just for now, that's what's happening here. Okay, so we've got a bunch of triangles here, and this will then allow us to simulate the flow. And what we're going to say is that the hydraulic head at this side of this block will be fixed at around 0.7, and at this side it will be fixed at around 0. Okay, so this is the high hydraulic head, and this is the low hydraulic head. And when we do the simulations, this is the distribution of the hydraulic head in the pore space. Okay, and here's the scale. And so if we were to draw in some contours, like we've been doing, the hydraulic head contour for 0.5 would be right around orange, right? So it would be there, and then here, and here. So not quite clear what it's doing through the solid space because there's no fluid there, but if we just were to dash it through there, you know, it might look like that. And then if we were to do something similar for, say, 0.3, that's this bluish, light blue, so it kind of comes through here, maybe something like that. And then this, how about here? Like right around 0.1 is going to be something like this. Okay, so those are the head contours. And locally, right here, the flow would be perpendicular to this, like that. But it's pretty complicated. Kind of bends around, and the reason for that is because the flow here is rather complicated. It's going to be going through this complicated geometry. So we can simulate what the flow paths are. And I don't know, maybe you can see that a little bit better. The flow's coming in here and then following these yellow paths. So it's kind of going around like that. Here it's coming like this. And here it comes in branches. And here it comes in branches and then comes back together. So keep that in mind. That'll have an important role in transport. But what we see here is that it's a fairly complex flow path system through this network of pores. So if we wanted to go and do a simulation at an aquifer scale, this is, say, a millimeter, right? We wanted to do this in an aquifer that was a few kilometers, then it would just be a huge amount of detail. It would be really impossible because we wouldn't really know what all these shapes were at the kilometer scale. So what we do is come up with an average so that if we take the hydraulic head here and here, we have a head gradient across this rectangle. And we can measure the average flux through this. And if we say that this rectangle has the same flux and the same head gradient as this one, then we've simplified the problem considerably because everything in here is uniform. The flow is straight, the head contours are straight, and we have just essentially an effective flow block that's replacing this one. Okay, so this, we would say that the flux is equal to the hydraulic head gradient times the hydraulic conductivity of this block. Okay, so the hydraulic conductivity that we assign to this block is representing the head loss, it's kind of the average head loss due to this complex flow geometry. Okay, so this is, last time we talked about the representative elementary volume. So this is a similar kind of thing. We had porosity was an averaging concept, and hydraulic conductivity is going to be an averaging concept as well. We use it to describe the average flux over an average hydraulic head gradient at a scale that's bigger than the pore scale. Okay, so we can do a simplified analogy of this where we use we go and we take the pores in a real porous medium, and this is one of those CAT scans we saw last time, and the geometry is pretty complicated. But what we can say is that we'll take these complicated geometries, the complicated pore geometries, and we'll represent them with an equivalent set of circular tubes, so that the head loss through this during flow through this set of pores is equal to the head loss through these circular tubes. Okay, so we have an irregular geometry. We can always, and we have some flow through that and some head loss. We can always then find a circular tube that has the same head loss for a given flow as this complex geometry. So that's what we're going to do, and we're going to represent these pores with these pores. Okay, so these are small tubes, small pores. So it's called a capillary tube, a small tube. And if we assume that the flow is laminar, which is going to be the case for a lot of groundwater flow, then there's a simple equation that's been developed for flow through a circular tube. It was done originally by this guy here, Pucelle. And it's called Pucelle's law. Okay, so Pucelle's law for flow through a capillary tube is going to be written like this. Okay, and that's the diameter of the tube. That's the unit weight of the water. We've seen that before. And this is the dynamic viscosity of the water. That's another property of water. So I have those terms labeled over here. Okay, I've written this as the flux, or as the flux. You could also think of it as the average velocity through that tube. Okay, so if we then think of the porous media as a bunch of these tubes, then we can write this for each one of those tubes. Okay, I mean, we could even do it for different diameters if we wanted, but let's just say for now that they all have the same diameter. Okay, so I recognize two terms from Darcy's law, relating the flux to the head gradient. Right, so I can write Darcy's law like this. Okay, and this is the hydraulic conductivity, and I think if I do that, then you can see that this thing here is the kind of the equivalent hydraulic conductivity to our network of, or our bundle of capillary tubes. So I could say then that K equals, and I have these little arrows here, so I want to write this in a certain way. Okay, so I'm just rewriting that and I mean, just kind of pulling things apart a little bit. So that's the diameter of the pore. This is the fluid, these are fluid properties. And this thing here, this thing here results from the pore shape. If we were to do the same analysis for a tube that was triangular, then that thing would be there. There would be a term that this is the diameter squared, right? So this is going to be proportional to the area of the circle, of that circle. If we did it with the triangle, there would be a term here that was the area, and then there would be a different number here that is from the shape. Okay, so this term controls the shape, the area, and the fluid properties. Okay. So let's rewrite this. So our capillary tube hydraulic conductivity is this. And in porous media, we don't really have circular pores, right? So this isn't going to be, strictly speaking, the hydraulic conductivity of porous media. The way we'll write it, though, is like this. Where this K, I think over here. So little k is permeability, big K is hydraulic conductivity. Okay, sometimes, in just common usage, those get used interchangeably. But really, for our purposes here, they're different. They're related, but they're not equal because of that term there. Okay, so what we see then is that K is going to be, I don't know, proportional or related to okay, so what we get from this analogy is that the permeability, it has units of length squared, and it's related to some kind of measure of the pore cross-sectional area of the pores and the shape of the pores. It won't be equal to that 32 because the shapes are complex. But what this means is that it's a measure of the porous media. Okay, so the hydraulic conductivity, it's a function of the pore area and the pore shape. So it depends on the porous medium. Hydraulic conductivity then from this, we see hydraulic conductivity, it depends on this and this. This is porous medium, this is fluid. Okay, that's fluid, this is porous medium. So we get kind of an interesting lesson here. Hydraulic conductivity, we said, was the flux per unit head gradient. So it's how much flow you get per unit of head gradient. Head gradient is how rapidly the energy is lost during flow through the medium. So hydraulic conductivity is the flux that you can get per unit of energy loss during flow. And what we see is that it depends on properties of the porous media and properties of the fluid. So if we have the same porous media and we change the fluid, then we're going to change the flow that we get per unit of head loss. That makes sense, you know? If we go from water if we have some sand and we have water flowing through it, we measure the flow and the head gradient, and then we put in some, I don't know, honey, going to have a lot less flow with honey because of with the same head gradient. Okay, so that is captured in hydraulic conductivity. In permeability, it just depends on the porous medium. Okay, so I can guarantee that I will ask on the exam, what's the difference between hydraulic conductivity and permeability? So the difference is hydraulic conductivity depends on the properties of the porous medium and the fluid, and permeability just depends on is a function of the properties of the porous medium. Okay. So dynamic viscosity. I think we probably have not yet seen this in this class. The dynamic viscosity, this is the viscosity, you know, in this kind of a simplified terms, it's how thick the fluid is. Well, I don't know. I guess in layman's terms, that's what it is. But there's a simple way to visualize it. So I want to do an experiment where I have, let me see. Let's say that this line here is the tabletop, and I put a slab here, and I have some liquid in here that the slab is floating, and this will be at the end of the table here. So I'm going to put a pulley here and attach a string and a weight. Okay, so this thing is I don't know, I guess it's floating or somehow sitting on top of the fluid. And then I put a weight here, and that weight is going to pull this thing along this layer of fluid. Okay, so as it does, it shears the fluid and creates a shear stress in the fluid. The rate at which it moves is going to be, we can write that as what's called as the rate of the shear strain. Okay, so I think you can see that conceptually what would happen is if this is a fixed weight, then as you change the fluid, as you go from water to honey, then it's going to move slower. So if we do this experiment, this is the shear stress, and that's going to be dictated by the weight. And then this is the rate of shear strain. So this is how rapidly this thing gets pulled along. So I think if we start out here at 0, if we add a small weight, then it goes at a small, we add a small weight, we create a small shear stress, and it goes at a slow rate. And then we add more weight, we get a faster rate, more weight, faster rate. Okay, and so the heavier we make this, the more shear stress we create in this fluid, and the faster it moves. Okay, and if we do this for water, then we get a straight line like that. Okay, and the slope of that line is the ratio of the shear stress to the shear strain rate. Okay, and that's the dynamic viscosity, that ratio. So if we did this for water, and then we changed it out and we did it with honey, we put a certain weight, and we're going to have, for a certain weight, we're going to have a slower rate, right? So honey would be there. Put on a big weight, and we just still have a small rate of movement. Okay, so we increase the viscosity, we go from water to honey, we increase the viscosity, and we increase the slope on that. See how that works? Okay, so that's the dynamic viscosity, and the plot here will be linear for water and for other fluids that are called the Newtonian fluids. There are fluids, though, where this is nonlinear, where it will go and curve. So if we think of the slope of this as the viscosity, right, then some fluids go linear like that, and then start to flatten out like that. So as you shear them faster and faster, the slope drops off, flattens out, and it behaves as if the viscosity is less. Okay, so got a feel for what kind of fluids do that. So often fluids that have solid particles in them will do that. One of the things they don't do that is behave like that is blood, or slurries of various types. And what happens then is as blood flows through your veins, or as slurries flow through pipes, the shear stress at the wall increases, and that causes the viscosity to drop. So you can have a fairly thick fluid move through a pipe or a tube much more easily than it would, well, if it behaves like this, and you can get up into this region at the wall of the tube, then it flows with much less head loss than it would if it was just linear. That's why blood can flow through small capillaries. And blood is pretty thick, but it can flow through small capillaries because it thins out like this. Okay, so there are quite a few fluids that do that. There's some fluids that curve up like that, but that's more rare. For our purposes, we'll be dealing really primarily with water, and so we'll be in here in this linear range. I'll talk to you in about a month about some work that I've done on hydraulic fracturing. You've all heard of fracking. So when you do fracking, you want to carry sand into the fracture to prop it open. And the way you do that is with with a fluid like this, you actually mix the sand in a very thick viscous gel. And that gel thins out when you pump it through, when you have the higher shear rate at the walls of a fracture. So more about that later. Let's go on. We've now got hydraulic conductivity and permeability, I think, under control. So take a look at some units. So we've seen hydraulic conductivity already. It has units of length per time. And in SI, meter per second or other units. The permeability saw that's going to be, in our simple term, we had it as d squared divided by 32. So it's going to be proportional to a length squared because it's related to the cross-sectional area of the pores. So the basic units are meters squared. And a unit that is used fairly commonly to describe permeability is the Darcy, from the same guy. And 1 Darcy is equal to that many times 10 to the minus 13 meters squared. That's pretty close to 10. So 1 Darcy is about 10 to the minus 12 meters squared. So those are the two main units. Sometimes you see permeability written in terms of centimeters squared. Okay, so I'm going to do the conversion here. So I'm giving you water. We just saw the dynamic viscosity, the kind of the description of it. The units that are used for dynamic viscosity is the poise, B-O-I-S-E, and that's from that guy Poiseuille. The viscosity of water is 1 centipoise, and that has units of 10 to the minus 3 Pascal seconds. And if we're going to go do this conversion, the unit weight of water in SI, the way that's going to be convenient to use the unit weight is in terms of, remember, unit weight is a force per volume, but we can also write it as a pressure per length. And so that's what I'm doing here, 9810 pascals per meter. So what I want to do is come up with a hydraulic conductivity when water flows through material with a permeability of essentially 1 Darcy. Okay, so 1 Darcy is kind of a nice baseline measure of permeability. So do 10 to the minus 12 meters squared. And then the unit weight, well, I'm going to go and do this. That's going to be pretty close to 10 to the 4th. So I can write that 10 to the 4th pascals meter. Then the dynamic viscosity is 10 to the minus 3 Pascal. So this is convenient because now the pascals go out and meters squared by meters, we end up with meters per second. And 10 to the minus 12 times 10 to the 4th is 10 to the minus 8. And then divided by 10 to the minus 3, that comes up. So this is going to be what, 10 to the minus 5 meters per second. Okay, So one of the things that we want to do is kind of get calibrated about different values of these important terms. So one Darcy, 10⁻12 meters squared permeability, and if water is the fluid flowing through it, it's 10⁻5 meters per second. And the difference between hydraulic conductivity and permeability, we already know. Good, right? Okay. Okay, so here's some values. This is in the handout. This is a log scale here, and this is in centimeters per second. So civil engineers like centimeters per second. And yeah, I usually use meters per second, but this table was in centimeters, so we can go with that. Right here, these are kind of three representative values. This is sand. This is a fine grained sand, is silt, and that's clay. So the permeability is this is minus log 10 centimeters per second. So this would be 10 to the minus 2 centimeters per second, or 10 to the minus 4 meters per second. This is 10 to the minus 5 centimeters, 10 to the minus 7 meters, 10 to the minus 9 meters per second. Okay, so those are some benchmark values. Let's do this. 10 to the minus medium grain sand. And the minus 4 meters per second. Fine grain silt, fine grain sand is silt is going to be 10 to the minus 7 meters per second, and clay 10 to the minus 9 meters per second. Okay, you can see the scale goes a good bit beyond these values and in the two directions. In general, hydraulic conductivity spans many orders of magnitude, right? So there's 11, so this is about 12 or 13 orders of magnitude. Really a big, broad range. This range here that I gave you for these typical values, this is kind of the more typical range of values that you see, but when you get into solid rock, you're down here, and when you get into very clean, coarse material like clean gravel, you're up in here. Okay, so there are various ways of estimating hydraulic conductivity. One of the simplest was, and really one of the first ones that uses a relationship between grain size and hydraulic conductivity, is the Hazen method. And you can see the date on that. And this method is, these are kind of empirical methods. And so Hazen did a bunch of experiments where he measured the grain size distribution and the hydraulic conductivity. So remember last class when we looked at the grain size distribution curve, both we had a curve that looked like this. And this was the size. We said that this was, this was the percent finer than, and 10% finer than with that size. That's P10. And the Hazen method says that you can estimate hydraulic conductivity from that size. And that there's a coefficient there. And then these other methods by Kozeny, Carmen, largely, and Combine, they're doing similar kinds of things, but they have other terms in there. But the basic idea here is that you measure the grain size and the porosity, things that are pretty easy to measure, and use that to estimate the hydraulic conductivity. One of the things that this points out is that you can estimate the hydraulic conductivity from this grain size. This is this is 10% is finer than. So most of the material is coarser than this side. This is just down at the tail on the spine side. But what it means is that the hydraulic conductivity is really controlled by this finer fraction in the grain size distribution. There are also various different devices where you measure hydraulic conductivity by taking a cylinder, putting it in this chamber here, having water go through it, and measuring head drop and the flow. Okay, so there's another term that comes up a lot. It's related to this, and what we'll see is that in a lot of cases, we're going to be interested in the flow that goes through a layer, sand layer or some kind of a permeable layer. And so when that happens, when we do the analysis, the hydraulic conductivity of the material in the layer multiplied by the thickness of the layer, that term ends up showing up a lot in the analysis that we'll be doing. So what's often done is just to lump those together into another term called the transmissivity. Okay, so transmissivity is the product of the hydraulic conductivity and the layer thickness. So we'll see some other things like this, where we have properties of layers and properties of material. So transmissivity is the property of this layer, and it consists of the property of the material that the layer is made of and the thickness of the layer. Okay, so now let's say we have several layers of material. Here's some layered sediments. And what's the hydraulic conductivity? What do we use for that? So I think that you can see just intuitively that if this was a sand and that's a silt, and sand and a silt, that the head loss, we have flow going this way, the head loss that we get per unit of flow would be less in this direction than in this direction. Because in order to go in this direction, the flow could take these higher permeability paths. And if that's lower permeability or lower hydraulic conductivity, just have less flow through there. But if we have flow going this way, the effective hydraulic conductivity would be less than it would be this way, because we would take more head drop to get a unit of flow. Okay, so what we want to be able to do is come up with a way to estimate an effective hydraulic conductivity in that direction. Often these layers are horizontal, so we call that KH, horizontal, and effective conductivity that way. And these conductivities, these hydraulic conductivities, we expect could be different. So when hydraulic conductivity, when a property depends on the direction, that means that it's anisotropic. So we want to be able to calculate the effective anisotropic hydraulic conductivity. So if we, and this is from another handout that I'll give you, but if we determine the effective hydraulic conductivity parallel to the layers, so we've got 3 layers. This will be K1 and B1. we want to determine the effective hydraulic conductivity parallel to the layers. And it looks like I'm calling it KP. Okay, so KE. What we're going to do, conceptually, what we'll say is the transmissivity, the effective transmissivity of this layer is going to equal the sum of the transmissivities of these three layers. So the transmissivity of this layer, there's B. Okay, that's T1, that's T2, that's T3. And just bring the BP over there. And we get then that the effective hydraulic conductivity of this layer is given by this. We can think of it like this. Okay, if you do it like that, then KE is like the weighted average, where the weighting depends on the relative thickness of the layer.
I
Okay?
have a question.
Seems to make sense. If we do the same thing in the other direction, so we take these layers here and rotate them like that. So we have flow in this direction. Here are the layers. Then we do it like this. Okay, so now I have flow like this going through these layers. There's one, two. So this is the transmissivity for this going parallel to layers. For this one, I'm going to say that the resistance to flow is equal to the thickness divided by the hydraulic conductivity. Okay, so the resistance will increase when the layer gets thicker or when the hydraulic conductivity gets less. So what we're going to do is say that the effective resistance is equal to the sum of the resistances of the three layers. Okay, so it's kind of a parallel to this. This is an effective transmissivity, this is an effective resistance. Okay, so we can then just do the substitution and say that the total thickness times the K effective vertical is okay, so I've just substituted the terms for the resistance in there. And then I need to solve for that. I get B, and it's going to be B. Okay, so that gives us the effective vertical conductivity. All right, so what I want to do is show you an example where we take a couple of layers and determine the effective vertical and horizontal hydraulic conductivity using these expressions that we've just developed. that'll be a good thing to start with next time. Good.